Good day, learners. Welcome to our mathematics lesson for today. My name is Snagile Ndlovu. This lesson is brought to you by Sci-Bono Discovery Center in collaboration with Gauteng Department of Education. In our today's lesson, we are going to be exploring some graphs on trigonometry. These are normally referred to as trig functions. You'll remember when we talk about trig functions, we are referring to sine, cosine, and tangent, those three. By the end of this lesson, you should be able to sketch a graph of any of the trigonometric functions defined by, let's say, f of x equals to sine of x, g of x equals to cos of x, and h of x equals to tan of x in the given domain. X is an element of negative 360 degrees to 360 degrees. That is a closed interval by using point-by-point plotting. These are standard trig functions. 2, you should be able to describe the function in terms of its amplitude, period, and frequency. 3, you should recognize and investigate the effect of the parameter k on the graphs of the functions defined by f of x equals to sine of kx, g of x equals to cos of kx, and h of x equals to k of x, tan kx. This k we are introducing in number 3 is referred to as a parameter. In other words, we are changing the size of the angle by either doubling it or multiplying it by 5 or multiplying by any number that we may decide to use there. In this case, we are only going to focus on positive k greater than 0. We may as well use k between 0 and 1, which is a fraction like half x, like a quarter of x, and so on. Right. Then by now, I'm expecting you to be familiar with trigonometry in general, where we defined the sine, cosine, and tangent in terms of the Cartesian plane. If you remember very well, we said last time sine theta is equals to y divided by r, and then cos theta is x divided by r. Otherwise, tan theta is y divided by x, talking algebraical on a Cartesian plane. We now know how to plot points on a Cartesian plane. Could be any graph. Plotting of points is very important so that you can join those points and see what kind of a graph they define. Then the general solution and particular solution of some trig equations. We are going to define just but a few terms here. We are going to look at the domain, range, the period of a graph, the amplitude of a graph. What do we mean by the domain of any given graph? Domain is a set of all the x values for which the graph is defined. In other words, as you plot that graph on a Cartesian plane, you are going to check whether your graph is using a closed interval or an open interval. Whichever way you interpret it, you must observe where your graph exists when you are moving across the axis, that is along the x-axis. Where is my graph defined? Where does my graph exist? That's what we mean by the domain of a given graph. Then the range, this time around we are focusing on the y side, which is the set of all the y values for which the function is defined. Then the period of these trig graphs. If you are studying trigonometric graphs, or you are exploring or working with trigonometric graphs, you will realize that they have what we call a cycle. They repeat themselves after a certain number of degrees. The same wave will repeat itself. This is what we refer to as the period of your graph. So the period of a trigonometric graph is the horizontal distance over which one complete cycle of the graph is completed. Then the amplitude of the graph of a trig graph is half the vertical distance between the highest point, which is the peak of your graph, and the lowest point of the graph. So these three are actually 4 of them, they are very crucial when you are studying these trigonometric functions. they will have a domain, they will have a range, they will have a period, as well as an amplitude. Right, we are going to be sketching some graphs today and comparing them and checking what we mean by domain, what we mean by range, what we mean by amplitude, and so on. So we are going to start by sketching standard functions. When I talk of a standard function, for instance, if I'm referring to the sine graph, if I'm given f of x is equals to sine of x, this is what we mean by a standard sine graph. How do you identify a standard sine graph? You'll always realize here that the coefficient there is a 1. It's always a 1 here, and then even here is a 1. That's what we mean by a standard sine graph. So we're going to sketch this graph and see how it's displayed on a Cartesian plane. What kind of a shape does it produce? And this time around, we are going to sketch it from a specified interval, which is our domain, x element of negative 360 degrees to 360 degrees, and it is a closed interval. In other words, this graph has been cut short. It starts exactly at negative 360 and must stop exactly at 360. We shall also have a look and see how do you show that this was a closed interval on a given sketch diagram. Right, after having drawn that graph, like in number 1, the question says, sketch the graph of the function f of x equals to 2 sine x in the interval x element of negative 360 to 360 in that closed interval. Having sketched your graph, you are expected to answer the following questions. The first question then says, determine the following: the domain of the graph f, the range of your graph f, as the period of your graph f, and the amplitude of your graph f. So for each particular graph that we are going to choose, we are going to focus on these 5 including the sketch itself. So after having sketched each particular graph, we would be interested in observing how is the domain of that graph, how is the range of that graph, how is the period of that graph, as well as the amplitude. So whenever you are drawing a graph using what we call point-by-point plotting on a Cartesian plane, you definitely require a graph paper. You also require a calculator, because you need to calculate the values of sine of each angle. And of course, you'll need a pencil for drawing your graph or joining your points, depending on what kind of points you are producing there. It could be a curve of some kind, so you need to curve around following your points until the sketch is produced. Right, so first things first, we'll need to complete a table. I've already given or designed a scale for you. Later on, I'll show you why I designed this scale using 90. I'm using an interval of 90 degrees. From 0, I'm moving to 90 degrees. From 90, 180, keep on adding 90 degrees until you get to 360. Some learners may choose to use 45, it will still work, but you can't use 180 for some reasons. You can't say 0, 180, 360, negative 180, negative 360, and stop there. There is a reason why you can't do that. We shall see as we proceed why that can't be done. So for now, I've already given you the domain is from negative 360 inclusively to 360. Then there are some missing corresponding values of our graph, which is our f of x. Indirectly, that f of x is basically your y. So we are given a function. The function says y is equals to sine of x. That is the function. Remember, f of x is equals to y. So our y is equals to sine of x. The x values have been given. What is missing are the y values. So I want you to, on your own, complete this table. I want to see how you are going to complete it. I'm going to give you some few minutes, at most maybe 1.5 minutes, to go through this table and complete it from negative 360 up until you get to 360 degrees, just by completing the table. Let's do likewise. Let's complete the table. Copy that table down and fill in the missing y values. Yes, you need to involve yourself. Let's get active there. Let's quickly copy that table down and work out the missing y values. You may as well use your calculator if you know how to use a calculator, and it's even faster using a calculator, wherein you can fit every little detail of that graph. Then you retrieve your answers straight from the calculator instead of substituting angle by angle until you get to 360 degrees. It might take longer. You should be familiar by now with a faster way of obtaining those y values upon drawing such kind of graphs. I'll just but wait for you to quickly do it. I want to see how fast you're going to do it. If you are having challenges there, we shall address them. You must ask questions, relevant questions, specifically to the drawing of these graphs. How do you quickly complete that table without struggling? You don't even have to struggle using your brain there. The calculator does everything for you. But the process of it depends. Maybe you might be substituting 0, substituting 90, and so on. Some learners might have a shorter way of doing it. Yes, I guess we are winning there. Right. Just for the benefit of those that are still struggling with the graph, by now I'm expecting you to have finished. This is how easily you complete this table using your calculator, depending on which type of a calculator you're using, but basically they are all the same. I'm using the right view type sharp. What you simply do there, you press mode on your calculator, and then you look for table. In my case, my table is under 2. I don't know, in your case it could be 3. As long as it is a sharp calculator, it can handle that. Then I will press my 2. The question is function. It means I must enter my function. I don't know what yours is prompting you to do there, but somehow you need to enter your function. Our function is sine x. And you have to hunt for x on your calculator there. It's either your x is orange in color or green in color. So you are going to use either second function to choose that x, or using alpha. So in my case, my x's are under alpha. So I'm going to say sine. You press sine. It will wait for you to enter sine of what is sine of a variable, because that x is representing different angles. So I'm going to say sine of x, which is alpha x or second function x. You must see on your screen sine of x. Then you enter. Your enter is your equal sign. You say equals to. Then some calculators may ask you to enter a second function, especially if you are drawing two graphs at the same time. But for now, I'm drawing one. I'll skip the second function. Some calculators say f of x. You fit f of x, which is sine x. Then enter. It will say g of x. You just skip that through saying equals. Then it will ask you, where do you want to start drawing your graph? This is where your domain comes into play. Your interval is negative 360 to 360. So you enter negative 360 degrees. Then you enter. It will ask you, what is your step? In other words, how do you want to space out your angles? My angles are spacing using 90 degrees. 0, 90, 180, moving towards the right-hand side. So I'm going to enter a step of 90 degrees. It means that's how I'm spacing out my angles. Then say equals. Once you say equals, it is automatically going to display a table wherein on one side it starts from negative 360, going down, up, increasing up to 360. Then on the other side, some calculators may say f of x, while other calculators may say answer. So it means when x is negative 360, our answer is a 0. So under negative 360, our answer is 0 there. Then the next one is a 1. The next one, 0. Then if you continue scrolling down, the next one is negative 1. At negative 90 is negative 1. Then you continue scrolling, it goes to 0, 0, 0. Sine 90 is giving me a 1 from my table. Then it continues. You can even check, it's now forming a pattern. 0, 1, 0, minus 1. 0, 1, 0, minus 1. But you can check from your table there. 180 is 0. Then 270 is negative 1. And then final 360, it goes to 0. That's how you can complete that table. You don't have to show calculations in these types of questions because the calculator can so long do the work for you. It's a question of knowing how to use your calculator. I'll repeat that process. You press mode on your calculator, and then from there it will prompt you to enter a function, either by saying function, it literally writes function 1. You enter your function 1, which in this case is sine of x, but fitting in that x might be a bit tricky. You check your own calculator, where is the letter x on your calculator and in what color does it appear. If it's orange, you use second function, depending on whether second function is orange or alpha is the one that is orange. If it's green, you check is alpha on my calculator, on yours it could be another color. So you press accordingly. Right. After you are done, what is very important is your domain. Where am I starting to fill in the table? We are starting from negative 360 and stopping at 360 degrees. Then from there, you command your calculator to move at a step of 90 degrees. 90 degrees by just entering step 90 and say equals. Then the calculator will display a complete table like the one that you see on your screen there. Then you transfer those numbers onto your table. Right. Having done that, you go to your Cartesian plane. There is our Cartesian plane. It's a graph paper. We want to draw our standard sine graph. So our x values are already given from negative 360 to 360. What is missing are the y values, which of course are trapped between negative 1 and 1. The maximum value of y we saw it was a 1 and the minimum was a negative 1. So we are going to plot these points point after point. Remember, we said our first point is negative 360 and 0. So you mark here negative 360 and 0. The next point is negative 270 and 1, which is above 270 and 1. The next point that we are going to mark is negative 180 and a 0. So it's coming down now. Then the next point is going to be negative 90 and negative 1. You mark all your points until you get to the last one, which is 360 degrees and 0 at the end there. Having done that, you are going to see all your points marked. Then you can see these points are forming a curve of some kind. Then you will draw your graph. It will produce a shape exactly like what you see, wherein this is your 90 and 1, and then this is your 180 and 0. After having marked all your points 0, 0 there, negative 90 and negative 1 should have been there, and so on. So at the end of the day, you are producing a wave of some kind. This is the behavior of the sine graph when observed between negative 360 degrees and 360 degrees, which is our domain. This is what we mean by our domain. Our graph starts from negative 360 degrees and stops at exactly 360 degrees. Then the question is, how do I know that it stops exactly at 360 degrees? You will realize that the end points are shaded. This is an indication that you are using a closed interval. If it's a closed interval, you lock your ends through shading. You shade your ends to show that it was starting exactly at negative 360 and stopping exactly at 360 degrees. So our x values are elements of x is an element of negative 360 degrees up to 360 degrees. So at the end of the day, this is the shape that we are producing. This is called a sine wave. It is called a sine wave. Okay. Now, having drawn our graph now from negative 360 to 360, what are you observing there? if we may quickly discuss this graph, what are you observing? Let's interpret our graph. What are we observing? I've already indicated that its domain is from minus 360 to 360. I can't talk about negative infinity to infinity. Why? Because this was not an open interval. That's why the ends are locked. How do we lock the ends? They are shaded. Otherwise, if it was an open interval, you put a ring, you don't shade it. It shows that it starts just after negative 360 and stops just before 360 degrees. That's an open interval. This one is a closed interval. That's why I'm shading the ends. Any other observation that we are making on the graphs? Yes, I can see, thank you. It starts from negative 1 and stops at 1. In other words, this graph is oscillating between negative 1 and positive 1. In other words, the wave is trapped between a maximum of 1 and a minimum of negative 1, meaning it is trapped between these lines there and there. It doesn't cross these lines. In other words, our graph is trapped. Its minimum is negative 1. The furthest it can go downwards is a negative 1. The furthest it can go upwards is a positive 1. Hence, it only exists between negative 1 and 1. What else are you observing? Yes, I'm realizing that it looks like there is a one complete wave. It stops at 0. It starts from negative 360. It starts from negative 360. If I may quickly look at that. Look at that. It looks like there is one complete wave, which is that yellow graph, connecting with another wave, which is that blue graph there. That's what I'm observing here. So it means that yellow graph is a complete wave. Then it starts again from 0, going up, crosses the x-axis, goes down, then comes back to the x-axis. The same behavior that it displayed coming from negative 360 to stop at 0. That's what we mean by a complete wave. Because when I bring this blue one, it's like it's the same wave that starts again. Oh, so I realize that between negative 360 and 360, I have two complete waves of that sine graph. It's the same graph that keeps on repeating itself. But the question is, after how many degrees does this repeat itself? From negative 360 to 0 is exactly 360 degrees. Then from 0 to 360 is another 360 degrees. So it shows me that this graph makes its complete wave after every 360 degrees. This is what we mean by the period of a graph. That's what we mean by the period of a graph. So between negative 360 and 360, you can have two complete waves of the sine graph. In short, there is only one complete cycle within a revolution. That yellow graph is a complete cycle and it happens within 360 degrees. There is one complete cycle within a revolution. From 0 to 360, that red graph, which I have shaded blue, is another complete sine wave within a revolution. Therefore, a standard sine graph completes only one cycle within a revolution. Meaning, after every 360 degrees, I have a complete graph. Okay, right, going back to the questions, they said we must determine the domain. We've already spoken so much on the domain. Is the values of the graph, x values of the graph where the graph exists. So our graph exists from minus 360. There is no discontinuity on the graph until we reach 360 degrees. In other words, it's one complete wave, one continuous graph from negative 360 up to exactly 360, although it comes in waves. It doesn't discontinue. Hence, the domain is negative 360 to 360 degrees, which can be written in two forms. Remember, it's inclusive. Negative 360 is less or equals to x. That x is less or equals to 360 degrees. That can be written in two ways. Then the range, we go back to the graph. The range speaks to the y side. We said our graph starts from negative 1 there and stops at 1. So our graph exists only between negative 1 and 1 for the y side. It doesn't go beyond 1, neither does it go below negative 1. It's trapped between those two lines. Right, so our range is negative 1 to 1 inclusively, because that's where it exactly starts and that's where it exactly ends. So our y values are trapped between negative 1 and 1 inclusively. We have already spoken about the period of our graph to say within a revolution, a cycle is completed. Therefore, our sine graph has a period of 360 degrees. This means we complete a complete wave after every 360 degrees. By definition, what did we say is an amplitude? An amplitude is half the distance between the peak of the graph and the lowest point of the graph. The peak of our graph is 1. The maximum that it reaches is a 1. From whichever position you look at, the maximum point is at 1. And the minimum is at negative 1. So what we mean by the amplitude simple means by how many units do we displace our graph sine away from the horizontal axis, the x-axis, either going up or going down. That's how we can define an amplitude. You have a baseline there, a line of displacement, which is your horizontal axis, the x-axis. If this graph decides to go up to the positive side of y, by how many units away from that line does it move? You will find that the furthest it can go is a 1. By the same token, by how many units does it go further down away from the same horizontal axis, x-axis? It's again a distance of 1, although that 1 is now on the negative side. It means we are moving one step downwards or one step upwards. So our amplitude, therefore, is defined as half the distance between the maximum value and the minimum value of the graph, which in this case is 1 minus negative 1 divided by 2, which will give us 1. This 1 is what we mean by the amplitude of a graph, which simply means how far up away from the x-axis do we move, how far below the x-axis do we move. Either side, we're moving by the same unit, which is just a displacement of 1 unit away from the x-axis. That's our amplitude. So in conclusion, what are we saying here? We are saying when you are drawing the sine graph from negative 360 to 360 degrees, it is going to make two complete waves, because within a revolution, it makes a complete cycle. It will have a range of negative 1 to 1. That's a standard sine graph. And its period will always be 360 degrees. Otherwise, its amplitude is always 1. Right, we are now going to move on. Having said so much on sine, we now have less work to do now on cosine, because they behave almost in the same manner, but we'll see as we proceed. The next question says, sketch the graph of cosine, given that g of x equals cos of x in the same interval. So what you'll realize as a difference as we progress from lower grades to upper grades, we'll realize that all the graphs that we have been drawing all along, we have been starting from 0 upwards. This time around, we are also looking at the negative angles. So we're going towards our left-hand side now. So our interval in this lesson is going to be negative 360 degrees to 360 degrees. We are again going to answer the same questions. We want to determine the domain of our graph. First things first, we want to see the nature of our sketch. How does it behave? Then we look at the domain, we look at the range, we look at the period, as well as the amplitude. Seemingly, it also has the same characteristics that the sine graph possesses. Okay. Again, we are going to start off by completing our table. This time around, you need to be a bit fast because you already know what to do. Step number 1, what did we say? Yes, we are going to say mode. Avoid saying cos to negative 360. You write down the answer. Cos negative 270, angle after angle is going to take forever or take longer. Rather, use the calculator. Get used to using the calculator as you are completing such tables. It's easier. The calculator is user-friendly at that moment. You go to your table, then function, this time you fit cos of x. You know where to find your x now, then say equals. Skip the function, second function, from the same domain, negative 360, enter. Then step is still 90, enter. Okay? Then you are going to get a table completed for you. I'm seeing negative 360 is a 1, followed by 0, followed by negative 1 at negative 180. You continue scrolling down, and then at negative 90 is a 0, and then at 0 is a 1. Remember, in sine at 0 it was a 0, and then at 90 is a 0. Seems it's opposing what the sine graph is doing. Then at 180 is a negative 1. At 270 is a 0. Guess the last number. Look at the pattern. 1, 0, negative 1. 0, 1, 0, negative 1. Next one, 0. After 0, yes, thank you, it's a 1. Well done. This is how we could have completed that table. Obviously, what is going to follow next is the plotting of those points, negative 360 and 1. You plot all your points up until you get to the last one, 360 degrees versus 1. It's again a wave of some kind. Although both ends are suspended, they are not touching the x-axis, whereas in the sine graph, those ends were touching the x-axis. It was 0 at 360 and 0 at negative 360. This time around, at negative 360, the graph is suspended there. It's also suspended here. Again, when we started this cosine graph, we realized that from negative 360 to 360, the graph is continuous. It's non-discontinuous. You can make one complete movement until you stop at 360. There is no way you can fail to define. You can pick any angle and say cos of that angle between minus 360 and 360. You'll always get an answer, which is the y side now. So this is a continuous graph between negative 360 and 360, which is our domain. Right, let's focus on a revolution now. We want to see after how many degrees does this cosine graph complete its cycle. Let's have a look at this. There is my first wave, that bell-shaped facing up. It's a complete wave already, because from there, from 0 up to 360, it's the same wave looking like the first one. So what does this mean? It means, again, there are two cosine waves within those two revolutions. After every 360 degrees, the graph is completed. How do I know that the graph is completed? This graph starts from 1 at negative 360. It goes down. It goes down until it reaches negative 1 at negative 180. Then it goes up and stops at 1 when x is 0, y is 1. It's a finished cycle. It's completed. Then from there, it behaves exactly the same way it started that blue graph. It goes down the same way it goes down on the other side. It goes down, it's like going down there. Further goes down, then turns, it goes up. Goes down, turns, then it goes up. So it shows that it finished its cycle at 0 from minus 360. Then another cycle starts at 0 and stops at 360 degrees. So we can clearly see again here that within a revolution, there is one complete cycle of a cosine graph. And what we are observing again here, on the sine graph, when the angle was 90 degrees, sine was 1. The value of y was 1 at that time. But this time around, when the angle is 0 degrees here, the value of the graph is 1. Those are the differences between the sine and the cosine. I'm not going to say a lot today based on how you can shift one and make it look like the other. That shall be addressed at some point in time. Right, so again, the domain is the same as the sine from negative 360 to 360. Remember, we said for this year, our domain is restricted to negative 360 to 360. That's the maximum domain that you can work with. Then the range, again, like the sine graph, is trapped between negative 1 and 1. So our graph exists between negative 1 there and 1 there. It doesn't go beyond 1 for the y values. It doesn't go below negative 1 again for the y values. Therefore, our range, the graph will exist only from negative 1 to 1. Otherwise, if you go below negative 1, you'll never see the graph again when you are moving across. If you go beyond 1, up on the positive side, you'll never again see the graph. In other words, the graph will never reach 1 comma something, 1 comma 2, 1 comma 5, 2, 3. It will never reach that. That's how a standard cosine and sine graph behave. Okay. Then the period again is 360. It looks like there's a lot in common. Their domain is the same, range is the same, period is the same, as well as the amplitude. Okay. Then we're moving on to the next graph, which is our tangent graph. This tangent graph behaves totally different from the other graphs. We shall see as we plot our points what happens on the tangent graph. Remember, tangent by definition, if you still remember your trick, as we were being introduced to some graphs, we said these three are related. Remember, tan of a graph is equal to sine of x, provided the angle is the same, divided by cosine of x. Keep that in mind. You'll understand why it behaves in a specific manner. Don't forget, tan of x is sine of x divided by cos of x. It will make you understand it better when you see certain things later. Again, we would want to know the domain, the range, the period, and as well as the amplitude. So first things first, we are going to sketch our graph by completing the table first. Quickly complete that table for me. This time I'm going to give you a minute to complete that table. Completion of a table should be straightforward. And you'll realize this time around I'm moving at an interval of 45 degrees. If you want to check the interval, you always locate 0 first, positive side, negative side, but focus on the positive. Is easier that way. 0, 45, 90, 135, and so on. It shows that we keep on adding 45. I still haven't explained why I'm using a 45 here and why I used the 90 for the other previous two graphs. I'll explain as soon as I finish this graph. I don't want to jump the gun. Okay? Right, quickly complete that table. Use your calculator. Those who have just joined, there is a special way of completing that table. And always make sure your calculator is in degrees, not gradients or radians. How do you test if your calculator is in the right mode? You can press sine of 90 degrees. We all know sine of 90 degrees is 1. So if your calculator kicks out something else, know that it's not in the right mode. You end up wondering why we are talking of 1, -1, yet you are getting something else. It means your calculator has been tuned into something else, either gradients or radians. That's another way of measuring English, radians. So always check, even in examinations, before you start using your calculator in trigonometry, always check that your calculator is in the right mode. It has to be in degrees. You can press tan 45 and see if it gives you 1. Then it shows that it is in the right mode, because tan 45 is 1. Then for those of us who have just joined us, this is how we're completing this table without taking one angle at a time. As you can see, there are a lot of angles this time around in the interval -360 to 360. You press mode on your calculator, depending on which type of a calculator you use. Then you press table. Then it will take you straight to f of x, meaning you have to fit your function tan of x. Our function here is y is equals to tan of x. That's the graph that we want to draw. And then you fit your function tan of x. You look for your x, alpha x, or second function x. Then you say equals. It will ask you for the second function, of which we don't have for now. You skip that and say equals. Then where do you want to start drawing your graph? That's your domain. -360 equals 2. Then the step, check your x values. Our step is 45. So you enter 45 and then say equals. You will realize that on this particular table this time around, there are some broken lines for specific angles. For example, at -270, there is no answer. It's just broken lines on your calculator. Those broken lines have a meaning. They are communicating with you. Right. Having completed your table, this is what I'm expecting. Tan of -360 degrees, I'm expecting a 0. And then -315 is a 1. -270 is undefined. All those broken lines mean is undefined. You can't get an answer, suggesting that probably the denominator is 0. Don't forget tan x is sine divided by cosine. And we saw earlier on cos of 270 is 0. I mean cos of -270 is 0. So meaning we are dividing by 0. That is an undefined situation. So the graph can't exist when it's -270. So you can clearly see at which points will I have what I call undefined, or lines of asymptotes. By now you know lines of asymptotes from even exponential graphs, hyperbolic graphs. These are the lines that the graph will never cross. It will get closer and closer to, but will never touch, because the y value does not exist at that time. You can't define it. So this is our table. Then from there, we go and mark all our lines of asymptotes on the graph and plot all the points as it were. -360 is 0. -270 is a line of asymptote. -180, the graph is crossing. You can pick any other angle between -270 and -180 somewhere here. You'll find that the y value is a negative there. You pick an angle between -180 and -90, you'll get a y value up there. So you'll find that there are some waves that are bounded by those red lines. The red lines are these lines that you saw earlier on. These are your red lines here. Those are your lines of asymptotes. So it means we are going to have vertical lines at negative 270, at negative 90, at 90 as well as and 270. So basically at plus or minus 90 is a line of asymptote, plus or minus 270 is another line of asymptote. Where is our graph crossing the x-axis? Where you see zeros is where the graph cuts the x-axis, just like any other graph. When a graph crosses the x-axis, y is equals to 0. So when I see a 0 on my table, it already suggests to me that this is where your graph is going to cross. When I see an undefined situation, like it's a broken line on my table, it indicates to me that the graph does not exist at that particular point. Okay, so at the end of the day, this is the graph that you are going to have. The graph will then get closer and closer, moving up and down towards our boundaries, which are those broken red lines. Those are called lines of asymptotes. These are our lines of asymptotes. This is a line of asymptote. Asymptote. We call them lines of asymptotes. These are the lines that the graph gets closer and closer to, but does not touch. So we realize that our tangent graph is a wave that is a snake-like going up and getting closer and closer to these lines of asymptotes. Is sigmoid in nature, is S-shaped in nature. It's an upside down S-shaped in nature. That's how the tangent graph behaves, but it's continuing to either direction. The graph is continuing, getting closer and closer, but will never touch those red lines. So these red lines are our lines of asymptotes. So between negative 360 and 360, there are 4 lines of asymptotes on a tangent standard graph. You will find one at negative 270, the next one is at negative 90, the next one is at 90, and the last one is at 270. In our restricted domain, we call this a restricted domain because we are not allowed to go beyond 360, neither are we allowed to go below negative 360. That's a restricted domain. It's our choice to start here and end there. It doesn't mean that all tangent graphs start at minus 360 and stop at 360. But for this lesson, it starts from minus 360 and 360. We want to observe the graph only between those two x values. So you can see again that it looks like this graph is the same wave that keeps on repeating itself. That black graph is the same wave that keeps on repeating itself. We can check after how many degrees it repeats itself. From 0 here, the graph will cross again at 180. From 180, it will touch again at 360 after every 180 degrees. That is our period. So the tangent of a graph has half a revolution period. In other words, it completes its cycle or wave after every 180 degrees, a new branch is born. After every 180 degrees, a new branch is born. And all these branches are trapped between special lines of asymptotes, those red lines. And again, if you look at those red lines, they appear after every 180 degrees. After every 180 degrees, meaning this gap here is 180 degrees. This gap here is 180 degrees. That's how it behaves. Same applies to the intercepts. It's also 180, 180. That's our tangent graph. Right, so the domain, like the other two graphs, is the same, from negative 360 to 360. Then range. This graph is unbounded on either side. It continues going further down and further up. So it's going to positive infinity from negative infinity. So we say our range is negative infinity is less than y, then less than positive infinity, with those two notations, either the inequality notation or the interval notation. But must be very careful here not to use less or equal for range, because you'll never reach infinity. So use an open-ended bracket. It's a curving bracket, open-end brackets. Then the period is 180 degrees. We've already explained that. I'm now interested in the amplitude. We saw with the other graphs, they were trapped between -1 and 1. It was easy to define the amplitude. But here, there is a problem. This graph forever continues and will never stop going up and going down. So we can clearly see that we can't find the amplitude here. Because for you to find the amplitude, is always half the distance between top minus bottom. And your top is, this graph doesn't stop. So where are you going to get your top minus bottom? So it shows us that we can't define the amplitude for this particular graph. So we say this tangent graph has no amplitude. It doesn't have an amplitude, because it forever increases and forever decreases. You can't say upper minus lower half that distance, because you'll never know the distance, because it doesn't stop. Neither can you say infinite. I know you are thinking of saying infinity minus negative infinity divided by 2, it goes back to infinity. Yes, that's mathematically correct, but you'll never know who is infinite. So when it comes to the tangent graph, the answer for amplitude is just no amplitude. Let's not try to be impossible and say infinity minus infinity divided by 2. No, it's just no amplitude. Okay. Right. In conclusion to these 3 standard graphs, you can see when I display all of them on one Cartesian plane, obviously they will cross at different points. They will meet at different points. Sometimes they coincide, meet at one point and intersect here, because each graph has got its own shape. But of interest is the sine and the cosine. Look at those 2 waves, the red and the blue. Yes, they look almost the same, meaning if I pull one back, it becomes the other, or I push the red forward, it becomes the other. But that's a topic for another day. For today, I'm just focusing on the standard. The standard sine and cosine, they oscillate between -1 and 1, whereas the tangent is unbounded. That's what I'm seeing. So what are we seeing? In the interval x element of negative 360 to 360, our period for the sine graph is 360, same as the cosine, whereas the one for tangent is 180 degrees. Our range for the first 2 graphs is the same. It's from -1 to 1 inclusively, strictly from exactly -1 and stops exactly at 1. Whereas for the tangent, remember we said it's running from negative infinity up to infinity, positive. That is the range. Then the amplitude for the sine is 1, for the cosine is 1, and for the tangent there is no amplitude. Then for the asymptotes, only tangent has got lines of asymptotes. Otherwise, the sine and cosine both don't have lines of asymptotes. And then for the lines of asymptotes, it's plus or minus 90 for the standard tan, and plus or minus 270. Then the interval spacing now. I used 90 for sine and 90 for cosine, as well as 45 degrees for tangent. The question is, how did I know that I must use 90, 90, and 45? Right, you'll remember we spoke, you can see the period. The period for sine is 360. there is a standard formula that we use to space out angles. It's called the interval spacing. You take your period of your graph. Now that you know the period is 360, you always divide by 4. Any graph that you are drawing, if you want it to come out perfectly, it was investigated and proven to be perfect. You take your period of that graph and then divide by 4. You will always know which angle you are using to space out. So in this case, if I take 360 and divide by 4, I get 90. So my interval spacing for sine and cosine is 90, while both have a period of 360. For tan, my period is 180. We saw the lines of asymptotes appear after every 180 degrees, or the wave appears after every 180 degrees. Then divide that by 4, you will get 45 degrees. That's why I spaced out my angles in the tangent graph using 45. It's a very, very important formula, especially if the graph paper has not been designed for you. You have to do it yourself. You always check the period of the graph, or rather of the function that you are drawing, divide it by 4. It's a standard formula. When I say it's a standard formula, it means someone sat down and used the 3, used the 2, used the 4, and eventually discovered that if you are using a 4, the graph comes out perfectly. So we take it as it is. That's your interval spacing. Okay. Then we now move on to the next part of our graph. But before we move on, we've already alluded to the fact that for the two functions, sine and cosine, both graphs have a period of 360 because one wave covers 360 degrees. Both graphs have turning points and intercepts with the horizontal axis spaced at 180 degrees interval. Maybe 90. Right, both graphs have an interval spacing of 90 degrees upon sketching. Then sketching of the graph, meaning when you're using the table function of the calculator, we select a step of 90. Then both graphs will have an amplitude of 1. Then for the tangent graph, intercepts with the horizontal axis and lines of asymptotes are spaced at 180 degrees. Wow, that's perfect. Okay. We proceed now and have a look at what we call the effect of the parameter k. What do we mean by the effect of the parameter k? It means I'm now going to change what was initially a 1. I spoke about a 1 earlier on. That 1 is going to change. As I change this 1, if it was sine x, that x is just 1x. I'm going to change that 1x and make it a particular number. Whether that number is going to be a fraction, positive fraction, or is going to be a simple whole number like 2 or 3, I'm changing that 1 to a particular number. This number that I'm going to introduce, we call it a parameter. So I'm going to use parameter k, you can use parameter p, and so on. I want to investigate and see. In my example, I'm going to use 1k throughout for all the 3 graphs so that I can compare with the previous graphs and see what effect does it have to include a number like 2x. Here is our first graph wherein we are introducing the parameter k. Again, it's going to take us back to point-by-point plotting. Sketch the graph of the function f of x equals to 2x. This time around, it's no longer 1x. It's now 2x there. I have introduced my parameter 2. So my k is 2. That's what I mean by parameter k. I have doubled the angle. It was just x in the previous examples. This time, I have doubled the angle and made it 2x. And I have chosen this interval, negative 180 to 360 for some reasons. Otherwise, I could have stuck to my original interval of negative 360 to 360. We are again going to focus on if we introduce a parameter, how is the domain affected, if it's affected? How is the range affected, if it's affected? We want to see who is affected amongst those 4: domain, range, period, and amplitude. Who is this K affecting of the 4 of us? That's what we mean by the effect of that K. Which one of the 4 is affected? Okay, so we'll start by completing our table. By now, you're in a better position. Then the question is, why did I use a 45 degrees there instead of 90? I'm not going to explain that until the whole graph is drawn. Then we shall see why this time around our spacing is 45, yet we are talking of a sine graph. We saw earlier in a standard sine graph has a period of 360. When you divide by 4, it comes to 90, meaning my spacing is 90. But here, my spacing is now 45. Okay, so you are going to complete the table. This is what I'm getting after completing my table. It's 0, 1, 0, -1. The pattern starts again at 0 degrees, 0, 1, -1, 0, 1, 0, -1. That's the pattern up until I get to 360 and 0. This time around, I decided to cut it short from -180 to 360. I didn't want to have a lot of angles given that my spacing is 45 degrees. It was going to be a very long table to complete. Okay, then from there, we're going to plot all those points from -180 up to 360 degrees. I want you to study that graph and have a look and see what is happening there, particularly from 0 to 360. I'm interested in these angles from 0 here up to 360 there, which is my revolution. What is happening in that revolution? I saw earlier on under the standard sine graph. This one is a new graph. Our new graph is y is equal to sine of 2x compared to the previous ones. We have doubled the angle. What do you notice? Yes, our domain is -180 to 360. Good. What else do you notice? Oh, look at the amplitude. Look at the range. Our range is still the same, -1 to 1. Okay. Our amplitude is still the same, is 1. Half the distance between the highest and the lowest is still 1. What changed here? Start that graph and see what changed. Because I think this too has an effect. Besides the spacing. There we go. The graph now has 2 complete waves within a revolution. Here are our 2. It's the green graph. It's a complete sine wave. Then the blue one is another complete sine wave. Yes, of course, there is the red one, but I'm focusing from 0 to 360. I want to start my graph within a revolution. What is happening within that revolution? With our original graph here. So from 0 to 360 degrees, what is happening? I realize that I now have 2 complete waves within a revolution. This means our sine graph has a frequency of 2 within a revolution. That green graph is a complete cycle on its own. This is my cycle 1. This is my cycle 1 of the sine graph. This is my second cycle of the same graph. My second cycle. So it shows us that our sine graph has 2 waves within a revolution. We call this the frequency of our graph. It appears twice within a revolution. So we realize now the effect of that 2 within a revolution on the sine graph. That 2 indicates that you are going to have 2 complete cycles within a revolution. So the first complete wave is from point A to point B. Then from point B to point C is another complete wave. And each wave has a period of 180 degrees. In other words, my graph is now completing its cycle faster than when it was a standard graph. In other words, we have increased the frequency of the graph. This is what we mean by increasing the frequency of a particular graph. So this is the effect of the parameter k. In this case, my k was a 2. This implies that I'm expecting 2 complete cycles within 1 revolution. In other words, the graph is moving faster to complete its cycle. It doesn't take longer like when it's 1. When that k is 1, it's a standard sine graph. It will take 360 degrees to complete a cycle. From A to B, the angle is 180 degrees. So I'm now going to talk about spacing, taking advantage of that spacing. The green graph has a period of 180, same as the blue, same as the red. If I divide this 180 degrees by 4, which we said is a standard formula, it gives me 45 degrees. Hence, I spaced my graph using 45 degrees. Then the question is, why is this period 180 and it's no longer 360? Remember, we're saying the frequency is what? Is 2. So that 360 must now be spread across 2 waves. So we're going to divide our period of 360 degrees, which is standard, by 2. Then it will come down to 180. It implies that that 2 has an effect of changing our period. It will also imply that there are now going to be 2 waves within a revolution. That's the effect of that 2 here. It's affecting your period and the frequency of the graph. So basically, there are 2 things that are affected here. The range is not affected. The domain is not affected. What is affected are 2 things. Is the frequency of the graph, meaning how many times will I see a complete sine wave within a revolution? I will see it twice. And what will be my new period, because it's no longer spanning across 360 degrees. It's now spanning across 180 degrees. So I will see it twice. Hence, 360 degrees divided by 2 will bring me down to a period of 180 degrees. Therefore, what am I saying? I'm saying domain is negative 180 to 360 inclusively, which can be also written in inequality form, but it has to use a less or equal symbol. Then our range still stays the same. The graph starts exactly at -1 and stops exactly at 1. Then I'm now worried about the period of this new graph, which is my sine 2x. Going back to what we said earlier on, here we have a period of 360 for a standard sine when it's a 1, not a 2. Now that I'm splitting that period into 2, it means each wave will have a period of 180 degrees. So in short, the new period of the graph is going to be 360 degrees divided by 2, it comes down to 180. Our sine graph will complete its wave within 180 degrees. It's done. Then a new graph wave takes over. So within a revolution, I'm expecting 2 of them. The amplitude stays the same. Therefore, dividing that 180 by 4 will give us 45 degrees, which is your interval spacing. Okay. Let's proceed to the next question. I'm still going to use the same parameter k equals to 2, but this time around I'm using it on the function of cosine. Same interval, same questions asked. Step number 1, you are going to complete your table. By now you must be having an idea where that 45 is coming from, because remember the sine and cosine, they have certain characteristics that they share. They have the same period, they have the same amplitude, they have the same domain in this case, and they have the same range. Probably that's why even when I introduce a 2 here, my angle of spacing is 45. You can confirm these values by using your calculator, like I explained earlier on how you use your calculator to find what is y when x is negative 180 up until you get to 360 degrees. Okay, are there any questions before I proceed? Right, if there are no questions, there is our sketch. Remember, even the original cosine graph, it was suspended there, and both ends are shaded, for the simple reason that it's a what? It's a restricted and closed domain from negative 180 degrees up to exactly 360 degrees. Again, we realize that the amplitude stays the same. Our period, I don't know, maybe it has been affected. We can check and see. Remember, the standard period is 360. I want you to focus on the positive angles from 0 up to 360 degrees and see how many waves of the cosine graph you can form there. It starts at 1 at the top, it comes down, it turns at 90 and negative 1. It passes through 135, 0, and it stops at 180. It's a finished or completed wave there. This is a complete wave. Then another wave takes over. Again, I realize when I start from 0, it stops at 180. That already suggests to me that the period is 180. Then from 180 to 360 is another wave. Therefore, again, I see 2 waves within a revolution. From A to B is a complete cosine wave. From B to C is another cosine wave within a revolution. Likewise, the graph has 2 complete cosine waves within a revolution. Hence, the frequency of the graph is a 2. The first wave is from A to point B, and the second wave is from point B to point C. And each wave has a period of 180 degrees, same as the sine wave after introducing that 2. That's another effect that we are seeing here on the cosine graph. There are 2 complete waves within a revolution. Oh, so that means if it's a 3, I must expect 3. If it's a 4, I must expect 4. Okay, something like that. If it's 1, I expect 1 complete wave within a revolution. Okay. Right, again, our domain is x is an element of negative 180 to 360 degrees, inclusively, using square brackets. And then our range is negative 1 to 1. Range is not affected, but period has been affected. You divide 360 degrees by 2, because if it's 1, the standard period is 360. But now that that 1 becomes 2 graphs in 1, they must split up that 360 into 180 and 180. So meaning our new period must agree with that. It must be now 180. These 2 you see here is that 2 that we introduced as a parameter. So whatever you introduce, you always break down that revolution using whatever number is given. If they put a half k, you divide by half. It means it is going to take longer to complete. If they give you k is a quarter, you divide by a quarter. You will see how long it takes to complete a cycle. But seemingly, when you put a whole number like 2, 3, 4 going up, seemingly the period gets smaller and smaller. So what does that mean? We shall see as we continue. Okay. Amplitude stays at 1. Right, let's move on to the last graph, wherein we are using our tangent function. It says sketch the graph of f of x equals to tan 2x in the interval x element of negative 180 to 180. I've deliberately restricted myself on the domain negative 180 to 180 for some reasons. Otherwise, if I maintain negative 360 to 360, it's going to be too many angles involved. All we are interested in is the behavior of the function. Otherwise, the domain does not really matter much to say how far I go on the x-axis. All I want to see is the behavior of the function, because the behavior that is going to display between minus 360 and 360 and between minus 180 and 180, if there is a pattern, that behavior will be consistent. It will be maintained. So I don't have to really worry much about the domain. Okay, again, we are interested in the shape. Does the shape change? For the last two we saw, the shape does not change. What changes is only the frequency and the period. Is range going to change here? Is period going to change? Is the amplitude going to change? Looking at the nature of the tangent graph. But seemingly from the first two that we have done, there are specific things that get affected by introducing this parameter k. You can also go and try your own questions wherein you change that k to a 3, change that k to a half, change that k to a quarter, something like that. Don't only work with whole numbers. You can even use fractional numbers and see how the graph gets affected, and see how the period gets affected, and see how many times you are going to see that graph within a revolution, if ever you'll see it. Okay. Again, we are going to complete our table from negative 90 to 90. I further restricted that for some reasons. Let's observe from negative 90 to 90, because the behavior will be the same anyhow. All right. That being the case, from negative 90 to 90, this is the behavior of your graph. There are some lines of asymptotes at negative 45, 45, oh, that plus or minus 45, negative 45, and positive 45. It becomes a line of asymptote. Remember the standard one, it was negative 90 and 90. Why is this one now at negative 45 and 45? Already you are seeing a 2 coming into play there, affecting the original in a way. Why was it at negative 90 last time? This time it's at negative 45. Maybe that's the effect of that 2 there. Okay. Then you draw your graph. You'll realize here that our lines of asymptotes are negative 45 degrees and 45. The graph crosses at negative 90 or touches at negative 90, as well as at 0, it cuts here. So when we start this graph, whether we're starting it from negative 360 to 360, from negative 180 to 180, from negative 90 to 90, the behavior will be the same. When I look at this distance here, if I span that distance there, how many degrees is that? How many degrees is that? This is exactly 90 degrees. It means our lines of asymptotes are spaced at an interval of 90 degrees. So if I want to know the next line of asymptote, I will say 45 degrees plus 90 degrees. which will give me 135. It will be my next line of asymptote. This will be your line of asymptote as the next one. Then if I subtract 90 from negative 135, on the other side, it will be now negative 135. Will be my other line of asymptote. Remember, we are saying it's plus or minus. If one is 45, the other is minus 45. If one is 135, the other is minus 135. That's how these lines of asymptotes are displayed on that Cartesian plane. Then the graph itself will exist. If you check, it cuts at 0 here. It cuts again at 90. Again, this intercept is after 90 degrees. Everything is happening after 90 degrees. What does this mean? It means the new period is now 90 degrees. The new period is now 90 degrees. That's the effect of these two in this tangent graph. So what gets affected are your lines of asymptotes. You divide by 2, the original lines of asymptotes. You divide by 2, you get new lines of asymptotes. Your period standard tangent graph has 180 degrees. Divide that by 2, it comes down to 90. So a tangent graph complete is cycling after every 180 degrees. So if it's now 2x, it will complete after 90 degrees. You are sharing that 180 degrees between two cycles of the tangent wave. Right, so in short, what are we saying? Our range, I'm not going to speak to the domain this time. Our range is negative infinity to infinity. This is the only graph that has such a range. Then our period, like we have already alluded to, this is 2x. So we're going to take the basic functionist period, which is always 180. We then divide by that 2, which is our parameter k equals to 2. We have introduced our k, which is equals to 2. When we divide the original period by 2, it will give us the new period for the new graph, meaning our tangent 2x graph, a new graph, will complete its cycle after every 90 degrees. Again, such graphs in tangent do not have amplitudes because they are unbounded. You can see it from there. They are unbounded. From minus infinity to infinity, therefore, there is no amplitude for a tangent graph. Whether it's tan x, is tan 2x, is tan 3x, is tan a quarter of x, is tan half x, there is no amplitude. You can't define it because the graph runs from minus infinity up to positive infinity. But what is important and what we must realize is that what is the effect of introducing a number other than 1 so that you are shifting from a standard trig function to a transformed function by introducing or changing the size of an angle through introducing a parameter, which is a number in this case. So these are the effects that we are observing here. Okay. Are there any questions before I proceed? Right. If there are no questions, this is what we observed in that interval, whether it's between negative 360 and 360, negative 180 and 180, the period of sine 2x is 180. The period of cos 2x is 180 also. Otherwise, the period for tan 2x is 90. It's like the original periods have been all divided by 2. That same 2 we introduced. We see the range stays the same as in the mother or original graphs. Some people normally call the mother graph. That's a original standard graph. Then the amplitude is 1, 1 for both, no amplitude for tan. you'll remember the asymptotes for the standard were plus or minus 90, plus or minus 270. This time around, our asymptotes are plus or minus 45 degrees in the interval and plus or minus 135 degrees, which is basically the original lines of asymptotes divided by 2, x values thereof. Then our interval spacing, initially it was 90, 90, and 45. This time around is 45, 45, and 22.5. Again, we have divided our period of the graph by 4, which is a standard formula for interval spacing. Spacing your angles on the given domain. So we are dividing 180 by 4, it comes to 45. We are dividing 180 by 4, we come to 45. We divide 90 by 4, we come to 22.5. Hence, we used 22.5 as we were drawing this new tangent graph after introducing the parameter k equals to 2. So in general, what am I saying? In general, we are saying for the functions f of x equals to kx and g of x equals cos of x, we know our periods are both 360. Whatever parameter you introduce, you divide 360 by k, then you'll know your new period. If k is 2, your new period will be 180. And the frequency of the graph will be 2, meaning it appears twice within a revolution. Then for the tangent, you are dividing the period 180 by k. If k is 2, the new period will be 90 degrees, and so on. That's the effect of introducing a parameter k to an angle. Then in general, what are we saying? The larger k values decrease the period. In other words, if you put a 3 instead of a 2, it will come further down to 60 for tangent. Otherwise, if you use a twist 90, if you use a 4, it comes down to 45. Then the smaller, in other words, which means the graph completes the cycle faster, because it's completing within 60 degrees now, not 180, neither 90. That's the effect of changing that k. The bigger the k, the smaller the period. The smaller the k, the bigger the period. The smaller the k values, they increase the period, which means it takes longer to complete a cycle. If you use 0.5 on 360, the sine graph or cosine graph will complete its cycle after 720 degrees, because you are using a very small number. It's a half a cycle within a revolution. So it takes longer to complete the cycle. So as you increase k, it becomes faster to complete your cycle. Frequency modulation, changing your frequency. Those are the effects of k to these trig functions. Are there any questions? Okay. If there are no questions, allow me to conclude the lesson by saying, in this today's lesson, we looked at how we sketch a graph of any trigonometric function defined by f of x equals sine of x, g of x equals cos of x, and h of x equals tan of x for within a given domain, x element of negative 360 to 360 by using what we call point-by-point plotting. 2, description of a function in terms of its amplitude, period, and frequency. Investigating the effect of the parameter k on the graphs of the functions defined by y equals sine kx, or y equals cos kx, or y equals tan kx, and discovered that for the functions sine kx and cos ax, the periods are reduced by dividing 360 by that k in sine and cosine, and dividing 180 by k in tangent. Otherwise, thank you for attending. We'll meet again at some point in time. Until then, have a great time. Study very hard. You shall conquer. Thank you.